Okay, so thus far we've learned all about wave functions, that they have these limitations, that they need to be continuous, they need to be square integrable, they can't go to infinity, they can't diverge. But why? What do we care, and how do we use this as chemists? So what I'm going to do is I'm going to apply the Schrodinger equation and quantized energy states, basically quantum mechanics, to two questions to a bunch of different types of systems. The two questions are, where are the electrons, or where are the quantized particle, or the particles that behave via quantum mechanics? Where are they, and what is their energy? Two questions. Where are they? What is their energy? And you can think of this as what is their position and what is their momentum? Noting that momentum is not energy, but thinking about, we want to know more information about our particle. So here we have the Schrodinger equation, the Hamiltonian operating on psi. This is our wave function, contains all the information. One dimension, we're just going to keep everything in one dimension for now, and we'll get to 3 dimensions in a little bit. So operator, wave function, eigenvalue, wave function. Okay, this is an eigenvalue equation, and I have written out here the total energy operator, the kinetic plus potential operators. Combine those together, you have the total energy operator, and that is your Hamiltonian. You will notice throughout these videos that I will be very specific in my language, and I will repeat myself over and over again, because this is probably a new type of mathematics that you haven't seen before. And so that repetition is going to be helpful in converting short-term memory into long-term memory. Go team. Okay, so the system that we're going to start with is a free particle. What does that mean? Let's draw it. Always draw your system. Free particle. It's a dot. It's a particle and it's free. It is not bound at all. Technically, at the moment, I am in my upstairs bedroom, or guest room, I guess, and I am bound to the walls of this room. I can, go towards the window, I can go towards the wall, but I'm going to hit a barrier. If I were a free particle, let's say, free to go anywhere I want to, I would probably need to be outside where there are no walls binding me to a specific location. So that's exactly what our free particle is. It's not bound anywhere. There's no boundary or potential energy that's going to block me from moving forward. So it's going to be free and happy to move any which direction. Okay. So the way that we use the Schrodinger equation to ask the question of what is this particle's position and what is this particle's momentum. So for free particle, the potential energy equals 0. Yay! Actually, that's not 0 factorial because that's 1. It equals 0, which means that the total energy operator, kinetic plus potential, is now just the kinetic energy. So all of the energy is going to be kinetic. None of it is going to be potential. And so we now have minus h bar squared over 2m second derivative with respect to x psi of x is equal to e of x, or sorry, e times psi of x. So the question now becomes, what wave function makes this statement true? What wave function here is such that if I were to take its second derivative and multiply it by h bar squared over 2m, I get that original function back again. Okay, so what makes this true? Well, if you look at how is this done section in Atkins, which is 7D how is that done 7D.1, it takes you through step by step. So hopefully you're watching this video, taking notes, and reading that section at the same time. Well, not the same time, but collectively together. Okay, so the way that we answer the question, which wave function is going to satisfy or make this equation true, is we guess. Now there's some hypothesis is an educated guess. We put some education behind this, and I'm going to kind of tell you which one it is, and then we're going to go back and verify that that's in fact the case. So psi of x is equal to a e to the ikx plus b e to the minus ikx. How would you know that? You would not. I'm not expecting you to be able to watch this lecture and say, oh yeah, that makes perfect sense. Of course that would be the one. You would have no idea. You would have no idea. But if it makes you feel any better, I would have no idea either when I first started working on this material. So this is something that we just know certain wave functions or certain functions are going to behave in a certain way. And you'll see in a second that if you take the second derivative of an exponential, you're going to get the function back again. So there's certain characteristics of functions that are going to fit the requirements that we have. There are certain characteristics of functions that are going to fit the requirements that we have. Those requirements are going to be what are called boundary conditions, and we're going to get more into that later. But that's kind of why and how we're starting the way we are. Okay, so let's check. Or let's verify that this is the case. So minus h bar squared over 2m d squared dx squared of this whole thing, ae to the ikx plus be to the minus ikx. Okay, so what I'm going to do down here is I'm going to take the derivative of just this section twice, and then I'll erase everything and we'll start from the two derivatives that we're going to solve for. So d dx of ae to the ikx plus be to the minus ikx is equal to, and I'm going to go and do this somewhat, not quickly, but thoroughly. For those of you in the room who need some help on derivatives, this is just good practice. So we take the derivative of this. This is the coefficient in front, the derivative of what's in the exponential, which is I times k. We're taking the derivative with respect to x. So the derivative of e to the x is e to the x times the derivative of whatever the x is. And so that derivative is ik times e to the ikx. Okay, do it again. Plus b times the derivative of up top. The derivative of minus ikx with respect to x is minus ik. So I'm going to make this a minus sign. Notice that I just erased the minus sign. Ik e to the minus ikx. Cool. That is derivative number one. Now derivative number two is d dx of this thing. The derivative of aik e to the ikx minus bik e to the minus ikx is equal to, all right, you do the same thing. The derivative of here is a times now ik times the derivative of ikx, which is ik, which gives us an I squared, k squared, e to the ikx minus, hopefully you can see this, b, same thing, minus ik times the derivative of minus ikx. Derivative of minus ikx is minus ik. So we've got minus and minus, that gives us back a plus. I squared, k squared, e to the minus ikx. I'm being very sloppy and going ahead and combining my negatives and positives. I would not recommend doing that, just so you can keep track of all of your negatives. It's very easy to lose them. All of you will lose a negative sign at some point in your homework. It is a rite of passage. It's okay. Just don't text me, email and or come to office hours and we'll find that negative sign. Okay, so this is now my second derivative of this function, which means this whole thing, box, is equal to this whole thing. So now I'm going to erase and rewrite this up top. Screenshot if you need it. Go team. Okay, so minus h bar squared over 2m I squared k squared, all that stuff. Good to note that the I squared is equal to minus 1, since minus I is equal to square root of minus 1. So if you square it, you get minus 1, which makes both of these a minus sign. So if that's the case, I'm just going to erase this and put a minus sign, and erase that and put a minus sign. You might want to rewrite it underneath. So what I can do is actually I can take out now k squared, or a minus k squared and a minus k squared. I can factor that out, which gives me a positive k squared h bar squared over 2m quantity a e to the ikx plus b e to the minus ikx. This is the left-hand side. Think about it. Left-hand side of the equation. So don't forget we've got h psi is equal to e psi. So I'm going to say now this is equal to e, and our psi was a e to the ikx plus b e to the minus ikx. And check this out. I have my original wave function now back on the right-hand side, which means e must be equal to k squared h bar squared over 2m. Groovy. What does this mean? This means that this function, or this statement, is true the Hamiltonian operating on the wave function that we proposed, a e to the ikx plus b e to the minus ikx, it does satisfy the Schrodinger equation and yields an eigenvalue k squared h bar squared over 2m and the original wave function again. Cool? So this does satisfy the Schrodinger equation. It is the energy of a free particle. And you'll notice something else that's really interesting. Actually, before we get there. So psi of x is equal to a e to the ikx plus b e to the minus ikx. Okay, those are x's. Okay, so let's double check. The requirements are psi. Psi has to be continuous. If you plot that, you will not get like a discontinuous, whatever it's called, point. So this is a continuous function. It has a continuous slope, which means its first derivative is continuous. It is single valued, which is good. So if you put any value in for x, you won't get two different values. Sorry, my nose is itching. And psi of x does not diverge, which means there's no way that this can go to infinity. Go team. Okay. Also, something really cool, let's look at the energy. So k can be any value. And you might think, well, duh, Allison, that doesn't make much sense. And the point is that in future systems, in the next video, we're going to put this particle, stick it in a box and see what happens, like me being stuck in this room for way too long. I hate COVID. Oh my God. Okay. So k could be limited, and there could be very specific values that k has to be. But in this case, we've got k can be absolutely any value because it's not restricted by any boundary, which is kind of nice. So therefore, what does this mean physically? This means the energy of a free particle is not quantized. Then why did we spend all this time doing this? Because as soon as we put this particle, where did he go? Why are particles he's? Let's make it a she. Let's make it a they, actually, is better. So as soon as this particle is put in a box, they're no longer restricted. Or sorry, they are not restricted. And so what happens, and if you take it out of the box, you open up all the access to the different energy states that are available. And so it is not quantized. The energy can be absolutely anything. So you have your little particle zipping along, and it's not confined to discrete energy states like we will see for electrons bound to atoms. Okay? What else do I want to say about this? Cool. Okay. So what can we do with this information? Well, what I want to do next, excuse me, I want to find what the momentum would be using this wave function. And in using this wave function, we need to break this wave function down just a little bit more. So this wave function is really a superposition of two wave functions. So we've got, and you wouldn't know this just by looking at it. It's not something that you could deduce. It's something that you would take what you know about particle systems and then apply it and then explore it a little bit more. So I'm kind of just giving this to you directly. I'm going to do that a lot in this class. In thermo, if you haven't had it, we're going to build everything kind of from first principles, or if you just had it, you remember like we did all of the math. Quantum is different. Quantum is, we're going to take pieces, but I'm going to give you a lot. So there's going to be a lot of assumptions that you're just going to have to make, or you're going to just take a lot of stuff at face value. And I apologize for that, but that's what grad school is for if you want to continue on into quantum. Okay. So this represents, so this wave, so this is a psi1 of x plus psi2 of x. So this can be looked at as a superposition where you have this psi1 is the positive x direction, and this psi2 is the negative x direction. So you have the particle going, let's say this is positive, x is going this way. So this psi1 would represent the particle going this way, and this psi2 would represent the particle going this way. Okay, so if you combine the two, you're going to have the particle going in both ways. But anytime you take a measurement, the particle is going to be in one of those spots, or going one way or going the other way. And this is where we collapse the wave function to be just that one particular wave function representing that particle at that instant. So if that's the case, if I want to say, well, what is my momentum? I'm going to take the momentum operator, which is linked to my momentum observable, which is minus IH bar d dx. Side note, you might also see the momentum operator is equal to h bar over I d dx. I'm a child of habit. I remember learning it this way, so that's what I do. But this is a good moment to say that 1 over I is equal to minus I. This is a relationship that's good to have in your back pocket. And so you'll notice that this is the same as 1 minus I, or 1 over I times h bar, which is the same as minus I times h bar. Those are the same thing. Go team. Okay. And if you're missing a negative sign, odds are that's probably where it is. So minus IH bar ddx is my momentum operator. So I can operate on, let's say I'm just going to operate on the positive x direction. If I do that, this gives me p hat operating on psi of x, which is equal to minus IH bar ddx of a e to the I kx. And that gives me minus IH bar. I take, there's my constant a, and I'm going to now multiply it by the derivative of the exponential, ik e to the I kx. Let's simplify this now. I've got an I and an I. That's a minus I. That's a minus, or that is a I squared, which is a minus 1. So this is I squared, which is equal to minus 1. So then I've got minus times a minus gives me a positive, k h bar a e to the I kx. Cool? So a single measurement, just one, would be using the eigenvalue equation of my operator linked to my observable. In doing so, that means I've got p hat operating on psi of x is equal to some eigenvalue of psi of x. So this equation satisfies the eigenvalue equation because look, I have my eigenvalue, positive kh bar, times my wave function back again. What this means is that this satisfies the momentum operator, and then my momentum observable would be kh bar for a single measurement. But I don't want a single measurement. I want a bunch of measurements. So I want to know what the expectation value of this would be. So I'm going to do the expectation value next. Okay, so we're looking at the expectation value of the momentum for this case. And so I've got the expectation value of the expectation value is the what happens when you take multiple, like a lot of measurements. And so you continuously, or not continuously, but you collapse the wave function via multiple measurements. And so what are you expecting to get? And so if we do this, we have integral of the complex conjugate of psi operating on p operator on psi dx, where our wave function is just the positive motion, or the momentum in the positive direction. And so this star here designates the complex conjugate, which means I'm going to take, now everywhere I see a complex number I, I'm going to replace that with a minus I. So I get a e to the minus I kx minus IH bar d dx, a e to the I kx dx. Okay. Same thing, I'm going to take the derivative again, a e to the minus I kx times minus IH bar. The derivative here is a times ik. Actually, I'm going to put ik times a e to the I kx dx. And I'm going to rearrange this a little bit, and you'll see why in a second. So I'm going to take these things out of the integrand, minus IH bar times I times k. My I times I gives me an I squared. So I've got I squared h bar times the integral a e to the minus I kx a e to the I kx dx. Okay, two things. First of all, minus I squared is a minus 1. Minus 1 times minus 1 gives me a positive 1. So this is just h bar k. Integral This is psi star. This is psi dx from minus infinity to infinity. All right, here's the kicker. Because I have a normalized wave function, which means if I were to try and find the probability of finding my particle between minus infinity to infinity, which means anywhere, I'm 100% guaranteed to find that particle, assuming the particle exists, of course, which means that this for a normalized wave function equals 1. Woo! So that's nice because I don't have to solve the integral. Most of quantum mechanics, and honestly, all of group theory is developed such that you don't have to solve any integrals. And in class, we're going to go over ways that you don't have to solve integrals by using the integral tables. Okay, so that means that p hat is equal to h bar k times 1, which means that the expectation of my momentum is equal to h bar k. Awesome! So this is a positive value in the positive direction. And so what this means is that I definitely have a particle going in the x direction, but it means that my minus ikx, my total superposition wave function, a times e to the ikx plus b e to the minus ikx, this one, the probability is 0 because it's not present because my particle is going forward. If I had a true superposition, it's possible I could have some probability of it going in one direction and some probability of it going in another direction. But when I take that measurement, when I take that measurement and collapse my wave function down, one of them will be selected and one of them will yield the outcome, which is the measurable, non-quantized momentum of a free particle. Go team! Okay, I hope this is helpful. I hope everything I do for you is helpful. But this is for a free particle. Now we're going to confine it such that our energies are now going to become quantized because those boundary conditions, i.e. sticking a particle in a box, as opposed to a particle being completely free to go any which direction it wants, as soon as you put a potential barrier, that changes the wave function, that changes the outcome. That's where quantum mechanics really takes hold. Cool? Particle in a box is next.